Welcome back to another lesson. This one oftentimes is a student favorite, L'Hopital's rule. We are going to be talking about limits, and that may or may not be exciting to you, but for whatever reason, I think the chance to use calculus to figure out some of the harder limits quickly is a really good feeling for people, because all of a sudden things that felt a little bit mysterious, there can be a nice set of steps to find them. And it's a beautiful circular relationship, right? Where limits gave us calculus, and then calculus, or derivatives rather, can help us do limits now. So we're paying it forward. Paying it back, we're paying it. So, L'Hopital's rule. There's a good question that you didn't know you should ask. How on earth do you spell that? Up here is a pretty common one. The hospital's rule. Often in French, or you'll see it maybe a little more correctly, would be with this little hat over the P, which basically says to do a soft S sound. L'Hopital's rule. Sometimes you'll see like a la, L-A, as if it was Spanish. I would say that probably this is the most correct. It's the most French. This is kind of an Englishification of it. And most people are okay with the little apostrophe there as opposed to a la. It looks like the hospital's rule, but it's L'Hopital. And the fun fact about L'Hopital's rule is that L'Hopital didn't actually invent it. He bought it off of a more famous, probably better mathematician named Bernoulli, and got credit for it. So I guess if he got paid, maybe it's okay? I'm not sure. I'll let you decide. But it still goes down under his name. Times used to be a little bit different than they are now. Okay, so let's think back to limits. We need to discuss something called an indeterminate form. So an indeterminate form is exactly those cases for limits where we had to keep working. So at least the most common ones, it's always a fraction, and it's when you try to plug in and you get 0 over 0, in which case, I don't know what that is, we have to keep working, or infinity over infinity, with a plus or minus is fine. Those are some of the most common cases where I would say, you can't just plug in and you don't know what that is. We should do some algebra to simplify it. But now we can not just do algebra, we can also do calculus to try to simplify it. So here is our first example. The limit as x goes to 1 of, I should actually add a little from the right, as x goes to 1 from the right of the natural log of x over x minus 1. So do you know what happens to the natural log of x as, oh actually I don't need that from the right. Let's get rid of that. Do you know what happens to the natural log of x as x goes to 1? What is the natural log of 1? Well, this is just going to 0. What happens to x minus 1 as x goes to 1? This is also going to 0. So it's a fractional form where the top is going to 0 and the bottom goes to 0. That definitely counts. Here is maybe a different looking one. Same thing, but now x is going to infinity. So natural log of x, what happens to the natural log of x as x gets really big? It goes off to infinity. X minus 1 as x gets really big, this also is going to go off to infinity. So this is another case of an indeterminate form, infinity over infinity. And in this case, it's going to be kind of a race to see which grows faster. So it is going to be important that you know relatively quickly how your basic functions behave. You need to know pretty quickly that as x goes to infinity, what is the end behavior? What is the asymptotics of natural log of x? Oh, it grows without bound, right? It goes off to infinity. There's no amount of knowing L'Hopital's rule that's going to make that faster for you, because you're going to need to decide, is this indeterminate or not? Okay, so let's get a real definition for indeterminate form. Here's our real definition. If I have a limit and I can write it as a fraction of two functions, f of x over g of x, then this limit is in indeterminate form if either of the following two things holds. The limit for f goes to 0 and the limit for g goes to 0. That's this 0 over 0 case. Or we also call it indeterminate if the limit for f goes to either plus or minus infinity and the limit for g goes to plus or minus infinity. This is also going to be the other case, that infinity over infinity case. Which of the following are in indeterminate form? Your first problem from this section. Take a second, see if you can tell. I'm going to cruise on right ahead. Sine of x over x this looks like, well, if I plug in 0 into sine, I get a 0. If I plug in x into 0, I get a 0. Boom, that is indeterminate form. All right, the limit as x goes to 0 from the right, well, natural log has a vertical asymptote there. This is going to negative infinity, actually, and this is going to 0. Does that count as an indeterminate form, infinity over 0? No, that's definitely not an indeterminate form. And so you would have to do something else. In fact, in this case, what you know for sure is that you have some kind of a vertical asymptote there, and you need to start doing your analysis of signs to say, is this going to positive infinity or negative infinity? In fact, this one is going to negative infinity without any extra work. Okay, and next up, looks like x, well, x is going to infinity. What happens to e to the x as x goes to infinity? That is also going to infinity. So this is definitely an indeterminate form. I like that a lot. How about this one? The top is going to 0. We really do need to pay attention to what's going on down here. And the bottom is going to 1. Right? So you, again, there's no substituting your knowledge of how these functions work. You need to know that e to the 0 is 1. If for some reason you think that's a 0, you're going to call this an indeterminate form. You're going to try to use L'Hopital's rule once you learn it. You're going to do a whole bunch of work, and you're going to get the wrong answer, which is the worst kind of wrong answer because you wasted a whole bunch of time. Really, what is 0 over 1? 0 over 1 is just 0. And you're done. Classic mistake for students just learning L'Hopital's rule is to try to use it everywhere and to not check or to not be careful about their indeterminate forms to make sure they can use it or they should use it. Oftentimes, if you can't, it's a sign that there's a really easy answer, that you're pretty close to the answer already. Okay, great. Let's go ahead and introduce you to L'Hopital's rule. It says the following. If you have a limit and you can write it as a fraction, you must try to write it as a fraction first. And it is in indeterminate form, then the limit that we cared about is equal to another limit. The limit that we get if we take the derivative of the top and the derivative of the bottom. It's like what you wanted the quotient rule to be, but isn't. Okay, so don't mix up this for the quotient rule. Don't start taking the derivative of the top and bottom separate when you want to do the quotient rule. This only works for L'Hopital's rule, that we can just compare the derivatives if we can't really compare the original functions. Quick note, this works for limits at infinity, so if a is infinity, it also works for one-sided limits as well, so going to a from the right. There's a couple ways to think about why this works. So one of them is just to sort of think about the linearization. So if I've got two different functions, and I want to know what's happening as they, at this point, say where they cross, maybe where they're crossing at the origin, something I could do instead is just to compare their tangent lines, their linearization, which is that linear approximation. Okay. So if they're crossing at the origin, then they have the same value there. And what I really care about is how fast they're getting to the origin. So if I were to compare the tangent lines, this amounts to looking for the slope of the tangent lines. This will tell you what that ratio is just comparing the two slopes. So locally they act like they look like their tangent lines, they look like their linearizations, and so if I say what would I do with their tangent lines, it would actually suffice to compare their slopes. And that's what L'Hopital's rule is saying. It's like, hey, just look at the slopes nearby. If they're in indeterminate form, that'll tell you what the limit is. A little bit hand wavy there. My apologies for that. I encourage you to think more deeply about it or try to look up a nice proof of it. The proofs are, it depends on how thorough people want to be on how nasty or nice that proof is. Next up, let's do some examples. Do a couple examples of the straightforward L'Hopital rule, and then we'll do some more complicated examples in a minute. So let's check. This, we started with this one before. This is going to 0, this is going to 0. We already said this is in indeterminate form. So L'Hopital's rule says, hey, let's take the derivative of the top. Do you know it? 1 over x over the derivative of the bottom. Okay. What I lost there was this limit. Make sure to include that. And there's also something else that's nice to do. It's nice to go ahead and write something like LR here, or even LH, to let the reader know that you're doing L'Hopital's rule, it can be very jarring to see some apparently totally different functions written down from what you did before. It's not always obvious the step that you took when you do L'Hopital's rule. So it's nice to kind of notate that with a little LR or maybe an LH to help your reader out. Okay. From here, we should usually simplify like crazy if we can, see if we can make any progress. So this is just equal to the limit as x goes to 1 of 1 over x over 1. That's just 1 over x. And that is just 1. Nice. Okay, so we got rid of those natural logs entirely thanks to that derivative. Okay, an old friend, the limit as x goes... Oh, I'm going to maybe change this one actually. This is the limit as x goes to 1 is what I wrote down over x. The problem with this is not an indeterminate form. Sine of 1 is not 0 and not infinity, and x is not 0, not infinity. And I kind of want to make sure I get this example in here with a 0. So now this should be an indeterminate form. This goes to 0, this goes to 0. Let's do a little L'Hopital's rule on it then, we're allowed to. Take this limit as x goes to 0, don't lose those limits. The derivative of sine is cosine. The derivative of x is 1. Look at how nice that is. One of the nice things about L'Hopital's rule is things like x's can turn into 1s, things like natural logs can turn into 1 over x's. So cosine of x over 1, if I plug in a 0, I get, what's cosine of 0? Just 1. Beautiful. And this is actually a pretty quick proof of the fact that the limit as x goes to 0 of sine of x over x is 1. And we use that limit to find the derivative of sine of x, actually, and it's used in several other proofs as well. It's a fairly important one. Okay, let's keep going. A couple more. Pause the video if you want to and give these a try. Looks like sine of x, if I plug in a pi, this goes to 0. If I plug in a pi into 1 minus cosine of x, I get 1 minus negative 1. So this goes to 2. Okay, what is 0 over 2? This is just 0. This was a trap. I tried to trap you. You should not use L'Hopital's rule here. In fact, you can't. If you use it, you'll get something wrong. So this is not an indeterminate form. So we can't use L'Hopital's rule, but also it's not an indeterminate form in such a way that makes our life really easy, as long as you know that 1 minus negative 1 is 2. So this is easier than L'Hopital's rule. We shouldn't be trying to use it. Okay, one more for kicks. This one's a little different. If I check, looks like the top is going to infinity, the bottom is going to infinity. That definitely counts. Let's do our old friend L'Hopital. The derivative of the top is e to the x. The derivative of the bottom is 3x squared. Okay, so now I'm going to try to plug in. And when I try to plug in, I notice that in the top, I still get infinity. In the bottom, I still get infinity. Wait a minute, that's an indeterminate form. We can do L'Hopital's rule again. And in fact, there's nothing to stop you from doing L'Hopital's rule as many times as you have patience for. So let's try this again. Looks like I get e to the x over 6x. And if I try to plug in again, I get infinity, and I get infinity. Right about now, I should ask myself, am I getting anywhere? Right? Is this helping me? And in fact, in this case, yeah, it is. Because each time I'm lowering my power on this denominator. And so I'm simplifying it. If I keep going, eventually I should get something sufficiently simple to just plug in. Let's go ahead and do it one more time. The limit as x goes to infinity of e to the x is still e to the x over 6. Now this looks like, well, positive infinity over 6. And we see, oh yeah, this is just going to be infinity. And in this interesting way, one, this is a nice example of how you can use L'Hopital's rule repeatedly if you need to. Second, notice how that e to the x just doesn't go away. It just hangs out forever. Whereas any polynomial is going to slowly lose the power until it becomes a constant and goes away. This is a nice example of how e to the x kind of just wins in these competitions. If you think of this as a fight between, or a competition between the numerator and the denominator, e to the x is going to stick around forever. But anything like a polynomial will eventually kind of work its way down to a constant and then 0. And this has everything to do with the fact that e to the x grows really fast in the long run. Exponentials grow very, very fast, much faster than any polynomial you can name. Okay, so quick reminder on the way out of this video, you must check for indeterminate form. You have to. If it's not in indeterminate form, there's probably a better way to do it, a faster way to do it. And also, there's nothing wrong with doing several L'Hopital's rule in a row. Next time, we'll see how you can massage certain problems that don't look like they're in indeterminate form into it to help yourself out in more situations.